Hi, I'm Ben-Yaakov. This presentation is entitled Ripple Steering in Coupled Inductors, the Coupled Sepic Case. This presentation was inspired by a paper written by Professor Chuck some times ago, 1987, in which he showed a way to do ripple steering, and I'm showing it in this presentation with regard to the Sepic converter. Now, there is a relevant video to this presentation in which I'm explaining this coupled inductor Sepic. So I suggest whoever is not familiar with the Sepic, please have a look at this video before you are watching this video that you are now looking at. I'm going to print all this information in the description section of the video that you are now watching. So here is a Sepic converter. We have the transistor, two inductors which are coupled. I'm talking about the coupled inductor Sepic converter. And this is a private case, of course. The inductances are 50 microhenry. And there is here a coefficient which makes one of them a bit different. Ideally, they should be the same value, but this is part of this ripple steering that I'm going to talk about in this presentation. So we have here the coupled inductor, and then we have an output. The advantage of the Sepic, of course, is that it has a gain transfer ratio smaller or larger than 1, which is nice, similar to the buck-box converter. So if we talk about coupled inductors in switch mode converters, we have to realize that coupled inductors are possible whenever you have a system in which the voltage across these inductors is equal as the two stages of the on and off duration. That is, otherwise you have here actually a short. If there is a voltage on one side which is different from the other side, the coupled inductors are actually a transformer. So if there is a big difference in the voltages, then of course it's a short and the current will be very high. So the basic requirement is, first of all, that the voltages will be the same. Some deviation can be accommodated, and they are actually taken care of by the leakage, which sort of take on the difference in the voltages. Now I'm talking about a 1-to-1. Of course, there are situations in which you may have other ratios. In the case of the Sepic, the nominal design will require that the inductances are 1-to-1, or the turns ratio also will be 1-to-1. Now, ripple steering means that we shift some of the ripple from one inductor to the other. Okay, so this is the idea of ripple steering, and by that we can reduce the ripple in one inductor. In this particular case, we'll be interested in reducing the ripple in the input inductor here, because here we're going to have at the output, in any case, we're going to have a pulsating current. So having a somewhat larger ripple doesn't make a big difference, but here, of course, without a ripple, it will be a DC current. And so the ripple here is important regarding EMI. So what is the basic idea of ripple steering? The idea is, again, to move ripple from one side to the other. As it turns out, to do that, you need to actually act on two fronts. First of all, you have to reduce the coupling coefficient, that is to increase the leakage. By that, you actually kind of control the ripple the way it develops. And there is another requirement, and that is to change the transfer ratio, the voltage transfer ratio between the coupled inductors. So you sort of control the ratio of the current of this transformer, okay? Because the current, of course, is related to the turns ratio, and if you change the turn ratio, you change the ripple current distribution between the two. Now, the issue of ripple steering is extremely complex. I don't know of any good analytical investigation which comes up with equations that you can actually predict exactly what's going on. And I'm not trying to do that. And the way that I'm dealing with it and showing it in this presentation is by simulation. That I'm going to show what is really happening when you change the coupling coefficient and the turns ratio vis-a-vis the ripple between the primary and secondary inductor. Now this I'm doing with this LT-SPICE schematics. Again, this is a Sepic contactor, coupled inductor. This is the coupling. Now I can change K as this is the coupling coefficient between the two, and also change this coefficient here, which is changing actually the turns ratio between the L1 and L2. Now the turn ratio is related to the inductances by square root. So if I have this coefficient Kk, then the turns ratio is square root of 1 over Kk. When it's 1, then of course the turns ratio is 1. And when it is smaller or larger than 1, then it is changing one way or the other. So here is just a run to see what is really happening. We see, first of all, the gate signals. And here are the ripples of the L1 and L2 inductors. These are sort of sinusoidal because we have here an interaction between the magnetization inductance and the capacitor. So we have sort of a smooth waveform here. But when you look at the ripple, you see that the ripple between the two sides is just about the same. This is for a tight, sort of a tight coupling, 0.99, and with this coefficient equal to 1. Okay? So ripples are the same, quite a bit. It's about 2 amp, I guess, peak to peak here. Now, if I change the coupling coefficient to 0.95 and this coefficient Kk, which is changing the turns ratio, to 0.9, you see that the L1 is reduced and the ripple of L2 doesn't change much, but the waveform is changing, and this is because now we have a larger leakage on which there is a voltage, so we are getting now sort of a triangular waveform. Now, using the step feature of LT-SPICE, I can actually scan the coefficient Kk for different coupling coefficients. So here I'm showing two cases, K equal to 0.95, which is sort of a moderate coupling, and here it's a better coupling, 9.8. And Kk now is sweeping between 0.8 to 1.2. I'm also showing here the RMS of L1 and L2. And you can see here clearly that when the Kk coefficient is 1, here it is here, then the ripple is the same. This is ripple peak to peak, the same for L1 and L2. But as you change this Kk larger or smaller, then you are shifting actually the ripple from one side to the other. And we see, for example, the L1, which we are interested in, if the Kk is 0.9, then from about 0.8 to 0.9 of a ripple, we go to 0.3, okay? Here, when the coupling coefficient is higher, the effect is much smaller. Changing now the coupling coefficient to 0.9, I can see that there is a dramatic change. This is when the coupling coefficient is 1. The value of the ripple, here I have this cursors now, is 0.9. So this is here. Now when the Kk factor is 0.8, we see that it goes down from 0.9 to 0.1 amp peak to peak, which is quite a bit. So we are talking about the 4.5 reduction factor between the balanced case to this case. So as I've said, I don't have an analytical explanation of what is going on here, but there's no question that by changing these two, the coupling coefficient and this factor Kk, that is the turn ratio between the coupled inductors, you can steer the ripple from one side to the other. The question is whether it's worthwhile and if the reduction ratio of the ripple is really significant. But there's no question about that this phenomena is very interesting and probably could be useful in some cases. So this brings me to the end of this short presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.